Okay, so thank you everyone for being here. And I'm going to be talking about the small deviation principle and Chung's law for some hypoelliptic diffusions. So let me just start by the general framework. So I'm interested in stochastic processes that takes values on Carnot groups. If you're not familiar with a Carnot group, you can just think of this as being, this is just Rn. Oh, that's kind of Rn. And then the usual way how we define the Wiener space on Rn, we define a Wiener space over a Carnot group simply by taking the set of continuous functions that start at the origin. And with this kind of setup, what do we mean by a small deviation principle? So we are basically interested in the following asymptotic here. So we take our process X. Again, if you're on Rn, this is just Euclidean norm. If it's in a Carnot group, there's a notion of homogeneous norm, but it's pretty much the same thing. And so you want to see when the probability that the max of this process is less than epsilon. And you want to figure out what's the rate of explosion of this function as epsilon goes to 0. This is also known as the small ball problem. And this is because simply you basically have the law of this one, the law of this process, which is a measure now on the Wiener space. And so you can rewrite this expression as in this way. Whoops. Mu of b epsilon. So basically the question is, you look at the law of the ball over this epsilon, where the ball in this case is taken with respect to the sup norm. Of course, there is nothing special about taking the sup norm. You can take any norm that you want on the path space. So to be slightly more precise, what we mean about the small deviation principle, we mean that we want to find some rates, some numbers, positive numbers, alpha and beta, such that the following limit is constant equal to c. And also we want this constant to be strictly positive and finite, so that alpha and beta actually fully characterize the asymptotic. So this is the first part. So that's the first part of the title. The second part of the title is Chung law. So what's the Chung law? This was it was first proven in 1948 by Chung for a standard Brownian motion. And so it basically looks at the following case. So you start with a process. Again, think of it as either Rn or a Carnot group, and then you consider this new process here. So the idea is that can we find a kind of law of iterated logarithm for the max of the original process? And what Chung proved, he proved that for a Brownian motion you can do that, and the actual rate here is the square root. So the constant a is 1/2. This is called the law at infinity, simply because you're taking limit at infinity. Same thing, you're going to ask for what's the behavior at time 0. And then if you think about it, for a Brownian motion, it doesn't really make a difference because you have Brownian inversion. So the behavior at time infinity is the same as the behavior at time 0, same rates and same constants. So these are the two things that I'm interested in. And let me give you some kind of useful tools, techniques that are very handful. In this case, first of all, we really like Gaussian processes for one main reason. So if you have a Gaussian process that takes values in Rn, then what you have is that if you look at its law mu, now mu it's a law on, it's a probability measure on this space. And we know that now we have a Gaussian measure on Banach space, and Gaussian measures on Banach spaces are very well understood. So there are techniques like Anderson inequality and like other things that can be used in this business of small deviations, which are very nice. The other property that we like is what it's called a scaling property, which simply means that if you look at the process at times epsilon t, that scales in a certain way. And of course, the equality here is in distribution. And why is this an interesting feature, something that you would like to have, is because if you do have this scaling property, then it's fairly easy to see that this equality holds. And now you see that basically on the left-hand side, what you have, it's kind of like related to the small ball problem. So you have this asymptotic here, and what you have on the right-hand side kind of resembles the Chung's law. So the punchline here is that if you have a process that does satisfy some sort of scaling property, you can kind of go back and forth in between Chung's law and small deviations. So what I mean is that if you can prove one of them and you have a scaling property, there is some hope you can prove the the other one, and it goes back and forth. Okay, so let me give you now some just general, like some known results. By any means, this is not a complete list. Let me also zoom a little bit. Okay, so the main kind of example is a Brownian motion where everything has been known for a long time. We know that it scales like root of epsilon, so we have a scaling factor of 2. You can prove using here probably semigroup theory, PD, that the small deviation principle is satisfied with a rate of explosion of epsilon square. So there's another 2 appearing here. And Chung proved in 48 that it satisfies this low value logarithm with a square root. So in some sense, what we see here is that there is some sort of like analogy between the scaling factor, the rate of convergence of the small deviation, and the rate of convergence of Chung's law. And this also happens for other processes. So the same thing is true for the Lévy area. This was proven by Rémillard in 94, where now the scaling factor is 1, and this is also the small rate, the small ball rate, and the Chung's rate. And again, another similarity is with the integrated Brownian motion, which was proven by Kozhniachev and Shi in 98, where now the process satisfies this scaling property here, and similarly they proved they provided the small ball asymptotics and the Chung's law rate. So this is for the rates. But another interesting thing is, what is the value of the actual constant when you take this limit? For the Brownian motion, this is well known as well. It's this number lambda 1. So what's lambda 1? Basically, so you have a Brownian motion in Rn, and now you take the Euclidean Laplacian, which is its generator, and then you look at the spectral gap of the Laplacian on a unit ball. So this quantity here is really the spectral gap of the Laplacian on the unit ball. And Chung's proved that you have the same thing. When you look at the Chung's law, you have the square root of the spectral gap. Pretty much a similar result was proven by Rémillard, where he proved that the limit is pi over 2, and he also gives some connection between this number and spectral properties of the generator of this process. The interesting thing is that nothing is really known for the integrated Brownian motion. So they prove that the limit exists, is strictly positive, it's finite, but there is the actual value is not known. And actually they point out that in general, in this business of small deviations, it's very hard to find the exact value of these asymptotics. So usually you're satisfied once you can get the rates and once you can prove that the limit exists. Okay, so that's kind of it for the general thing. So let's see what I was interested in. So my advisor, this is a joint work with my advisor, she suggested me to look at the horizontal Brownian motion on the Heisenberg group. So first of all, if you're not familiar with the Heisenberg group, think of it as being R3. So it's really just a non-abelian version of R3. And again, it's a Cournot group, so there is a nice norm on this space. And also, what is this horizontal Brownian motion is a very explicit expression. So its first 2 components are just a standard Brownian motion, and its third component is the Lévy area of the first 2. Pros and cons. This is not a Gaussian process. So basically, all the techniques that are known for Gaussian processes don't really apply here. Or on the other hand, also the underlying space, the Wiener space here, is not a Banach space. I mean, it's an infinite dimensional space. It has it's complete with respect to some natural norm, but it's not a linear space. So we don't have the Banach structure. But on the other hand, what we do have is that we have the scaling property. So what we did here was, okay, let's try to, basically having this scaling property here suggested us what the correct rate should have been, just by looking at the other examples. So we kind of knew that the right rate should have been the square root here. So we were able to prove the Chung's law first. And then what we did, we basically went back to a couple of slides before when I told you that if you have the scaling property, then pretty much you can go back and forth between Chung's law and the small ball problem. So basically what we did, we used Chung's law plus the scaling property to prove the small deviation problem here. And this was was funny because it was really, we had the opposite issue that usually of the usual issue. So when you're working this business, proving the existence of the limit is it's not easy, but like it's not too hard because you can really use a lot of properties of Gaussian measures. So that we couldn't do. But then usually the hard part in this business is once you have the limit exists, you want to prove that it's strictly positive and finite. And that's usually hard. So for us, it was like fairly easy to prove that the lim sup here is finite and the lim was positive. But what was kind of challenging was how do we prove the existence, and that we use the Chung's law. And then here, yeah, there's also Chung law times 0. That again, this one you get it for free, because basically this process here also satisfies a sort of like Brownian inversion. So you get it from the Brownian inversion. Also, let me turn the light on because sorry, but it's getting dark here. Okay, so this was the first process. The second process that I looked at was the Kolmogorov diffusion. So here, there we go. So Kolmogorov diffusion is just, it's a two-dimensional process. Its first component is a Brownian motion. Its second component is an integrated Brownian motion. And the main reason why I wanted to look at this process is that it doesn't have a scaling property, where here I'm looking at the standard Euclidean norm. And so I was kind of curious to see, oh, what kind of, it wasn't clear what rate we should expect. But what we were able to prove is that you still have, Chung's law and small deviation. And the interesting thing is that now the rates are different. So we've proved that at time infinity, the Kolmogorov diffusion really behaves like an integrated Brownian motion. So in some sense, when the time is getting like larger and larger, this guy really is the second component is the one that is leading. Whereas for small times, the behavior is the same as we have a square root, which is the same as the Brownian motion. So for small times, we have the first component is the leading one. And I think I'll just I'll stop here. Yeah, thank you.